Right now, without moving, you are within arm's reach of it. It is in the frame of whatever you are sitting on, in the screen you are looking at, in the building around you, in the cells your body uses to carry oxygen. Iron is so ordinary that it has stopped being a material and become a background condition. It is also the fourth most common element in the crust of this planet, roughly 5% of everything under your feet. It is in the red clay of a riverbank, in the rust-colored stones of a hillside, in the soil of every continent. And for 200,000 years, humans walked over all of it and could not touch a single gram. Worse than that, when our ancestors finally did build a metal age, they built it out of the rarest thing they could possibly have chosen. Tin makes up about 2 parts per million of the crust. 2 parts per million. Our species located that, dug it out of a handful of deposits scattered across the planet, and shipped it thousands of kilometers, while standing on ground that was 5% iron the entire time. So here is the question. Why does the hard, common, useful metal arrive 2,000 years after the soft, rare, difficult one? What was actually stopping them? And when iron finally shows up, why is the first version of it worse than the bronze it replaced? Every layer of this gets stranger than the last. Let's go. Let's start with what a metal actually has to survive to reach your hand, because that one problem explains the whole order of events. Almost no metal sits in the ground as metal. It sits as ore, which is metal chemically locked to something else, usually oxygen or sulfur. Malachite, the bright green stone people ground up for eye paint, is copper bonded to oxygen and carbon. Rust-colored hematite is iron bonded to oxygen. The metal is right there, and it is held shut. To open it, you need 2 things at once: enough heat and a chemical thief. The thief is the part people forget. Charcoal in a sealed hot space does not simply produce heat. Starved of air, it produces carbon monoxide, a gas that is desperate for oxygen and will pull it off almost anything it touches. That gas walks up to an iron oxide, takes the oxygen away, and leaves metal behind. So a furnace is not a hot box. It is a chemical argument, and heat is only one side of it. Nobody sat down and worked that out. The first smelt on this planet was almost certainly an accident, and we can point at the room it happened in. Potters had been running kilns for thousands of years before anybody made metal. A pottery kiln is a sealed clay chamber packed with fuel, deliberately starved of air to control the color of the finished pot. In other words, our ancestors had been building perfect little reduction chambers, over and over, for a completely unrelated reason. Now add the pigment. Malachite is that vivid green copper ore, and people ground it for eye paint and body decoration across the whole ancient Near East. It was a cosmetic, traded and valued long before anybody cared that it contained metal. Put green pigment into a hot sealed kiln, by accident, as spilled powder or as decoration on a pot, and the carbon monoxide does what carbon monoxide does. When the kiln cools, there are small beads of red metal sitting in the ash. That is the entire beginning of metallurgy, not a genius. A spill, in a workshop built for something else, repeated by enough people in enough places that somebody eventually noticed the pattern. Now put the 2 metals side by side, and the whole sequence explains itself. Copper melts at 1085 degrees. A decent pottery kiln, which our ancestors already had, reaches that. And copper has an enormous advantage because it also occurs as native metal, sitting in the ground already in metallic form. There are lumps of it in Michigan and Anatolia that a person could simply pick up and hammer. No chemistry needed at all. Iron melts at 1538 degrees. No ancient furnace on Earth reached that. Not one. That temperature was not achieved industrially until the medieval period in Europe, and iron had been in use for 2,500 years by then. So on the face of it, iron should have been impossible. And that is exactly what everybody assumes was the problem. It was not. Here is what is fascinating. You never actually had to melt iron. You only had to convince it to let go of its oxygen. At around 11 to 1200 degrees, well inside the range of a charcoal furnace with bellows, the carbon monoxide gets to work. The iron oxide gives up its oxygen. But because you are hundreds of degrees below melting point, the iron that appears does not run out as a liquid. It arrives as a spongy, glowing, porous mass, riddled with holes and mixed through with waste, sitting in the bottom of the furnace. That mass has a name, a bloom, and a furnace built to make one is a bloomery. What comes out is not a usable object. It is a heavy, ugly, half-rock lump of iron and slag welded together. To turn it into metal, you have to reheat it and hammer it, then reheat it and hammer it again, driving out the trapped waste a little at a time over hours, and you lose a large share of the mass while doing it. And the waste tells you everything about how hard this was. Every smelt produces slag, the glassy rock that forms when the non-metal parts of the ore melt together and run down. For every kilogram of iron a bloomery makes, it leaves behind several kilograms of slag, and slag does not decay. It sits in the ground for 3,000 years exactly where it was tipped. That is why ironworking sites are some of the easiest things to find in archaeology. You are not looking for the metal, which rusts away to nothing. You are looking for the mountain of glassy waste beside the workshop. In parts of Africa and Europe, there are slag heaps holding tens of thousands of tons of it, built up smelt by smelt over centuries. Stand in front of one of those heaps, and the true price of iron becomes obvious. Every ton of that waste represents a furnace built and broken open, a week of charcoal, and a person hammering a glowing lump until their arms gave out. So the puzzle was never the temperature. The puzzle was that iron demands an enormous amount of expert labor after it comes out of the fire, and copper does not. Some of you are already thinking, hold on, ancient people had iron long before any of this. Fair question, and it is exactly right. They did. It just did not come from the ground. It came from the sky. In a cemetery at Gerzeh in Egypt, archaeologists found tube-shaped iron beads strung with gold and stone. They date to around 3,200 years before the Common Era, which is roughly 2,000 years before anybody was smelting iron anywhere. For a century, people argued about what they were. Then in 2013, a team including Thilo Rehren put them under a scanning electron microscope. The metal contains around 30% nickel, with a distinctive banded internal structure. Terrestrial iron does not look like that. Meteoritic iron does, every time. Those beads were cold hammered from a lump of a meteorite, worked slowly at low temperature into thin sheets and rolled into tubes. Somebody found a strange, heavy stone that had fallen out of the sky, worked out that it responded to hammering, and made jewelry from it. And the most famous object in the world confirms it. In 2016, a team led by Daniela Camelli examined the dagger from Tutankhamun's tomb with X-ray fluorescence, without taking a single sample. The blade is about 11% nickel and carries cobalt in the ratio you find in meteorites. Think about what that means for the value of iron at that date. The richest ruler of the richest kingdom on earth, in a tomb stacked with gold, was buried with an iron blade because iron was more precious than gold. It was worth more because it fell out of the sky, and nobody could make more of it. There is even a word for it. Egyptian texts of that period use a term that translates roughly as metal from the heavens. And the supply explains the price. Iron meteorites are rare arrivals, and a usable one is rarer still. Almost all of them are an alloy of iron and nickel, which is why the nickel signature is such a reliable fingerprint. Some carry a crystal structure formed by cooling over millions of years in space at about a degree per million years, a pattern that cannot be faked and cannot be produced on Earth. There is a second reason meteoritic iron mattered so much. It arrives already metallic. No ore, no furnace, no chemistry. You could work it cold, slowly, with the same hammering technique people already had for native copper. Across the entire Bronze Age Near East, the total number of known meteoritic iron objects is small enough to list. Beads, a few blades, a headrest, a bracelet, an amulet. Everything on that list is a grave offering or a royal possession. Nothing on it is a tool. So iron does not begin as a tool, it begins as a jewel. Now here is the part that turns the entire story over, and it is the reason the timeline looks so wrong. The first iron was worse than the bronze it replaced. Sit with that, because everything you assume about iron comes from a version of it that arrived much later. Pure smelted iron, straight out of a bloomery, hammered clean, is soft. Measured on a hardness scale, it comes in around 80 to 100. Properly worked tin bronze comes in at 150 to 200, sometimes higher. A bronze sword holds an edge better. It casts into a mold, so you can pour 100 identical blades. It does not corrode into orange flakes when it rains. Bronze is, by almost every measure that mattered to a person in the year 1500 before the Common Era, the superior material. Iron is harder to make, needs more fuel, requires vastly more hammering, cannot be cast, and rusts. And bronze had something iron could not touch for another 2,000 years. You can pour it. Melt bronze and it becomes a liquid you can cast into a shaped mold. That means repeatability. One craftsman carves one mold, and after that the workshop produces 100 identical spearheads, axe heads, cauldrons, and fittings, each one the same weight and the same shape, made by people who do not need to be masters. Iron in a bloomery never becomes liquid, so none of that is available. Every single iron object has to be hammered individually into shape by somebody who knows what they are doing. A bronze workshop scales. An iron workshop does not. Look at what that meant for a palace. The archives of the late Bronze Age are full of metal accounting. Letters between rulers negotiating shipments. Inventories listing weights of copper and tin down to fractions. A wreck found off the Turkish coast at Uluburun from around 1300 years before the Common Era was carrying about 10 tons of copper in oxhide-shaped ingots and roughly a ton of tin, along with goods from at least 7 different cultures. 10 tons on one ship. That is what a functioning bronze economy looked like, and it is why nobody in it was interested in a lumpy gray metal you had to beat into shape by hand. So the real question is not why iron took so long. It is why anybody switched to it at all. And the answer has nothing to do with the metal. So, what ended it? What ended 2,000 years of bronze being the obvious choice? A supply line. Bronze is copper plus tin, roughly 9 parts to 1. Copper is common enough, tin is the problem. Those 2 parts per million are not spread evenly. They are concentrated in a very small number of places, and in the ancient Mediterranean world, almost none of them were local. The tin came from Afghanistan, from Central Asia, and there is now solid evidence that some of it came from Cornwall, at the far western edge of Europe. It moved by donkey caravan and by ship, through a chain of middlemen, across thousands of kilometers, over borders controlled by a dozen different powers. That means a bronze sword in Greece was the end product of an international supply chain running most of the way across the known world. Every palace economy of the late Bronze Age depended on it. Egypt, the Hittites, Mycenae, Ugarit, Assyria, all of them, all connected, all trading, all writing to each other about shipments. Then, over a few decades, either side of the year 1200 before the Common Era, that entire system comes apart. Cities across the eastern Mediterranean are abandoned. Palaces are emptied. The writing systems of Mycenaean Greece fall out of use entirely, and the region goes silent for centuries. Ugarit, a wealthy trading city, is left and never reoccupied. The historian Eric Klein has spent a career arguing that no single cause explains it, and that what you are looking at is a tangle of them. Drought, migration, conflict, and system failure, all arriving together on a network too interconnected to survive any of them. And here is the cost of that, in numbers. The trade routes that carried tin thousands of kilometers stop functioning. A metal that was already rare becomes, for practical purposes, unavailable. Bronze does not vanish. What vanishes is the ability to make new bronze at scale. Meanwhile, iron ore is lying in the ground in every single one of those regions. Not shipped, not taxed, not dependent on anybody's goodwill, in the hillside behind the village. That is the moment iron wins, and it wins for the least romantic reason imaginable. It is not better, it is local. Some of you know the other version of this story, the one where the Hittites hold a secret iron monopoly, and the technology escapes when their empire falls. Fair question, because that version is in a lot of books. The evidence has not been kind to it. Smelted iron fragments turn up at Kaman Kalahoyuk in central Anatolia, dating to around 2,000 years before the Common Era, which is centuries before the Hittite Empire existed at all. Iron objects appear scattered across the Near East through the Bronze Age in small numbers, in several places, with no sign of a single controlling source. and the Hittite texts people cite as proof of a monopoly read much more like a king apologizing that usable iron is in short supply, which is not how a monopolist writes. The monopoly story is tidy. The real pattern is that several regions had the knowledge. Nobody could do much with it while bronze was flowing, and then the flow stopped. And we can put numbers on exactly how hard the alternative was, because people have rebuilt these furnaces and run them. Experimental archaeologists have fired reconstructed bloomeries hundreds of times now, and the arithmetic is brutal. A single smelt takes a shaft furnace roughly 1.5 meters tall, built from clay, which often has to be broken open to get the bloom out and then rebuilt. It needs somewhere between 20 and 40 kilos of charcoal for a run of 8 to 12 hours. Producing that charcoal takes several times its own weight in wood and about a week of separate work. At the end of all of it, a successful run yields a bloom of a few kilos, and after all the hammering that removes the trapped waste, you may be left with 1 or 2 kilos of usable metal. Now scale that up. Equipping a single group of fighters with iron means weeks of charcoal production, a forest's worth of wood, and an expert who knows exactly how much air to push and when to stop. That is why iron was not a shortcut, it was a trade. You gave up the international supply chain and paid for it in local labor and local trees instead. What if the Iron Age is not a story about a better metal at all? What if it is a story about a network failing and a civilization being forced down to whatever it could produce inside its own valley? What if the thing we call progress here was, at the moment it happened, a downgrade that people accepted because the alternative was nothing? Because that is what the material record shows. Early iron objects are not triumphant. They are patchy in quality, often more decorative than practical, and for a long stretch they sit alongside bronze rather than replacing it. Iron only becomes the material we think of when somebody works out the next step, and that step is carbon. Hammer iron in a charcoal furnace long enough, and the surface picks up carbon from the fuel. A little carbon, between about 0.5% and 1.5%, and the metal transforms. Now it can be hardened by heating and quenching, and it goes far past anything bronze can reach. That is steel, and it is an accident of the process rather than a plan. The forge was already full of carbon. Somebody noticed that iron worked a certain way, came out harder, and started doing it deliberately. And this was not one place. Iron smelting appears in West Africa, at sites in Nigeria associated with the Nok culture, from around the middle of the first millennium before the Common Era, with furnace designs that are not copies of anything to the north. Whether that is independent invention or transmitted knowledge is still argued, but the African furnaces are their own tradition, with their own solutions. The African furnaces deserve more than a footnote, because they solved the problem differently. Some of the shaft furnaces excavated in West and Central Africa are tall, built to run on natural draft rather than on somebody working bellows for 10 hours. A well-designed tall shaft pulls its own air through, which changes the labor arithmetic completely. Others used preheated air, drawing it through the hot walls of the furnace before it reached the charge, which pushes the temperature higher for the same fuel. Iron production in parts of Africa ran continuously for well over 2,000 years, and in some regions it was still running as a living craft into the 20th century, which is why we have direct records of how it was actually done, rather than guesses from excavation alone. And then there is the last step, the one that finally makes iron worth all of this. Steel is iron with a small amount of carbon in it, between roughly 0.5% and 1.5%. Below that, it stays soft. Above about 2%, it becomes cast iron, hard but brittle and will crack rather than bend. Getting into that narrow window was not a recipe anybody wrote down. It came from the forge itself. Iron held in glowing charcoal absorbs carbon from the fuel at the surface, slowly, and the longer and hotter you work it, the deeper that layer runs. Smiths noticed that metal treated one way came out harder than metal treated another way, and started repeating whatever had worked. Then comes quenching. Heat carbon-bearing iron to glowing and drop it into water, and the internal structure locks into a hard, brittle form. Reheat it gently afterwards, and you trade some of that hardness back for toughness. That single sequence is the reason a steel edge beats a bronze edge, and it took centuries of accumulated craft to arrive at reliably. So the honest answer to how ancient humans discovered iron is that they discovered it several times, mostly by accident, in the bottom of furnaces built for something else, and then ignored it for 2,000 years because it was not worth the effort while bronze kept arriving. The discovery was never the hard part. Every potter firing red clay in a charcoal kiln was standing next to the beginning of it. What was hard was the reason to care. We traded a beautiful, reliable metal that arrived from the other side of the world for an ugly, difficult one lying in the dirt outside, and most of us never even knew that is why everything after it was possible. So put your hand on the nearest piece of iron. The chair frame, the door hinge, the screw in the wall. Somebody found the first of it in a lump of rock that fell from the sky and treasured it more than gold. So tell me in the comments, what is the closest piece of iron to you right now? And did you even notice it before I asked?